Okay? All right, so yesterday we talked about just the overview. Today we're going to go a little bit more in depth about the three types of bonds. Okay? Covalent bonds, we said, were what are they doing with their electrons? Sharing. Sharing is caring. Don't be ionic, be covalent. Okay? Some of the vocab you need to know for covalent bonds are, if you have a covalent bond stuck together, we call that a molecule. Okay? It's a neutral group of atoms that are held together by their covalent bonds. When we're referring to the compound, we call it a molecular compound. Okay? And that is the simplest form is the molecule. That's the simplest that we can break it down. And then, of course, the chemical formulas are going to be used for both covalent and ionic, but the chemical formula is where we use the atoms and the subscripts to tell you how many are present. So yesterday we said sugar was a covalent compound, and we said it was C12H22O11. And so that's telling us that in that one molecule, there were 12 carbon, 22 hydrogen, and 11 oxygen. So that's what that's telling us. Remember, the subscripts only count for the one that comes right before it. Okay? Only count for what comes right before it. Okay? We're good there? Before I move on? The diatomic molecules are the molecules that are... Why didn't this switch? Oh, there we go. Nope, too far. This one's not working for a second. So remember our diatomic molecules, we talked about it a couple of units ago. It's going to be very important throughout the year. Those are your Brinkelhoffs that we talked about. Remember, that means that they are stuck with another one just like them. Okay? For instance, oxygen. When you have oxygen in the atmosphere right now, it's an O2 molecule. You actually won't find oxygen floating around in just an atom. Okay? It forms a molecule. Same thing with nitrogen, which is the bulk of air. It's N2. Okay? So those are always stuck together, okay? Yesterday we said if something's bonded to itself, we said it was what kind of covalent bond? Nonpolar. Nonpolar, you are correct. Nonpolar. Because they have the same electronegativity, so the difference would be 0. Okay? Formation of a chemical bond, we said yesterday, it's the nuclei and the valence electrons of another atom, and they are attracted to each other until the optimum distance is reached, because they are trying to have the lowest potential energy possible. And so that when that is like the sweet spot, that's going to be the bond length. Okay? All right, everybody good there? Okay. Give you a second to write. Okay. Characteristics of the covalent bond. We said the bond length. Okay, that's going to be a definition you need to know. The distance between two bonded atoms at their minimum potential energy. Okay. Bond energy is the energy required to break a chemical bond to form back to its neutral isolated atoms. So if I wanted to break up H2O, there is a bond energy for the hydrogen to oxygen bond. Okay, those have been studied and they're published values. You can look that up. At the end of the year, we'll do thermochemistry and we'll talk about bond energies, and we'll use those bond energies and calculate. But we don't do that this time. You just got to know what bond energy is. Okay. The octet rule is basically, we've been saying this all along. What's everybody trying to get to? 8, because 8 is great. Okay. So the octet rule states that compounds tend to form so that atoms, either by gaining, losing, or sharing electrons, reach their octet. Okay, in their outer energy level. And the outer energy level is where? Outermost what? But which configurations? S and P. We're looking at the outer S and P. Okay. However, there are some exceptions to the octet rule. And that is boron can only get 6. It'll only get a total of 6. It only has 3 valence electrons, okay? So it will share those 3 valence electrons for a total of 6, okay? If you look at where it's located on the table, it only has 5 to begin with, so it doesn't have an octet underneath. So even if it was to, it can't gain 6, that's too many. I mean, can't gain 5, that's too many. So it tends to share, although it sometimes will give away 3, okay? But it's a metalloid, and metalloids are special, and they can do different things, okay? Hydrogen and helium also are not going to get 8. They're only going to get 2 max because they only have an S sublevel. They only have a 1s, and so they can't gain more than 1. And of course, helium, it's not going to do anything, right? It's already got its 2, which is completely fills its outer shell. So helium is a noble gas, and it won't. But and then there are some that can form more. Sulfur and phosphorus are 2 good examples. They can actually get more than 8 sometimes. It's called an expanded octet. They get like 8, 10, 12, some of them. Then that's what makes chemistry fun, is all these exceptions, right? Y'all are not agreeing with me. Okay. Electron dot notation. Okay. This is going to be a way that we present just the valence electrons. Because the core electrons aren't doing anything, right? They're just hanging out, and what's going on? Let's watch this party happen. Okay? So we care only about the valence electrons. So we draw those as electron dots. And again, we're only looking at the outermost S and P. So we have, this is going to be all of the ones in period 3. Okay? So period 3, sodium's the first one. It's in group 1. How many valence electrons does sodium have? 1. So we draw 1 dot. That doesn't really look like a dot. Let's try that again. 1 dot. Huh? Okay, I'm glad you asked that question. Do I always have to start on the left? No. Okay? It doesn't really matter which side we start on. If I stand there, I'm right in your way. I'm sorry. It doesn't matter what side we start on. Okay? You just got to put 1 on there. I just have it. Okay? Magnesium is the next one. It has how many valence electrons? 2. So we put our first one. Now this one does matter. Okay? I have to put it on the opposite side because I want to minimize. Remember, we're trying to minimize those electron repulsions. So just like when Hund's rule stated everybody had to get 1 before they got a second one, same thing here. Everybody, each side's got to get 1 before I can give it a second one. Okay? Boron, how many valence electrons? 3. So we're going to go 1, 2, 3. We're going to give them all on each side. And then carbon. All right, so now each one has 1 side, so now we can start pairing them up. How many valence electrons does nitrogen have? It's in group 15. 5. So now we're going to say 1, 2, 3, 4, and we can pair it up. Again, it doesn't matter which side you put the pair on, just because there's only 1 side that has a pair. Okay? Then comes oxygen, which has 6. So 1, 2, 3, 4, 5, and 6. Again, doesn't matter as long as when you pair them up, they're opposite from each other. And then fluorine.
7.
And it doesn't matter where you leave that open spot, just because remember, we're drawing them in 2D on our paper, but in actuality, they're 3D, so it doesn't rotate them around. And then neon is our noble gas, finishing out group 18, so it has an 8, has a complete octet. So basically, wherever you see an open spot that's not paired up is where they can form bonds. Okay? These two are metals. Will they share? Metals always give them away. So those actual dots, they're going to kick out. So those are not going to share. But these the last of these, where you see an open spot is where they can form a bond. So boron can form 3 bonds, here, here, and here. Carbon, here, 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 and here. So you can see how many bonds that particular atom needs. How many bonds will nitrogen? 3. It's got 3 open spots. And then oxygen has 2. And fluorine has 1. And neon has none. And that is typically how many bonds they will form. Okay? So we're going to need that as we go through and draw Lewis structures. So today we're going to talk about Lewis structures. Next week we're going to do something called molecular geometry, and we're going to find out the shapes of these molecules. Okay? And then once we get through this unit and the naming unit, if you want to get started on your next project, you can, but you can't do it yet because you don't know all the stuff. Some people have looked ahead and you can't really start that project yet. Okay? So the way that we draw Lewis structures is we're going to use these dots or dashes to indicate where a bond happens. So the best way to do it is draw your electron dot of the individual and see where they would join up. So hydrogen has how many valence electrons? 1. Okay, and how many did fluorine have? So guess what? This is going to go there, and they're going to share, because these are both non-metals, so they're sharing. So we can draw that like this. We can show them sharing their electron. Or we can draw it as a dash, if you would like. I prefer the dashes. I find the dots tedious, so I prefer the dashes. But when I draw a dash, how many electrons am I representing? 2. So make sure you understand that. So now we check, well, we know hydrogen's an exception. It can't have 8 electrons, so it can only have 2. So it's got its 2. And then fluorine needs 8, so does it have access to 8 electrons? Yes. Okay, so by sharing 1 with hydrogen, it now has access to 8. Okay, so hydrogen would look like this, or like this. It's going to share those 2 electrons. And then what would fluorine look like? Okay, or we could draw it like this. I don't like the dots. They're tedious. And on this, I have trouble drawing the dots because if I try to make just a bigger dot, it like thinks I'm trying to like expand it and it does weird things. So that's why my dots are messy. Okay? So that's how you do Lewis structures. We're going to do a lot more of that next week. The lone pairs are the unshared pairs of electrons that are not involved in the bonding. Okay? So we drew this fluorine a while ago and we said fluorine looks like this. And we had these extra electrons around it. So these are our lone pairs. They belong only to that fluorine atom. Okay, same thing on the other one. They are only sharing these right here. So they're only sharing 2. The other 3 sets of electrons are called lone pairs, and they belong individually to those individual atoms. Okay. The structural formula is similar to the Lewis structure, except we don't have to draw all the tedious dots. So we would just say dash, dash, and dash. Because we are assuming that you know that they have those valence electrons or those lone pairs. Okay? So that's the structural formula. We like the structural formula better. I hate the dots. I hate the dots. They're not annoying. Okay? So far we've shown you single bonds. Okay? Single bonds are sharing 1 pair of electrons, or 2. 2 total, 1 pair. Okay? Some elements can actually form multiple bonds. Okay? And the ones that are the most common to do that, because they share more than 1 pair, are carbon, nitrogen, oxygen, and sulfur has that ability as well. Okay? So those are the most common ones that can form double bonds. So double bond is sharing 2 pair of electrons, and so it actually forms 2 bonds. So again, let's draw these individually, their electron dots. So carbon has 4, right? Because it has 4 valence electrons. How many does oxygen have? 6. Okay? So carbon has to have 4 bonds. Okay? Carbon always, except for in the case of carbon monoxide, carbon always has to have 4 bonds. It only has 2 oxygen available to bond with it. Okay? Luckily, oxygen needs 2 bonds. So what they do is they form a bond here, and then here and here. So that ultimately it looks like this. Okay, so that's what carbon dioxide structurally would look like. So each oxygen would have 2 lone pairs that belong only to it, but carbon doesn't have any lone pairs. Okay? Carbon never gets lone pairs, okay? Except in carbon monoxide. It's weird. Okay? Carbon always gets 4 bonds, whether it's a 4 single, a double double, or a triple and a single. Okay? but it never has lone pairs. Huh? What did you say? Okay. Sorry, I thought you asked a question. So that's what carbon dioxide and double bond would look like. Triple bonds are sharing of 3 pair of electrons. Okay? So nitrogen has how many valence electrons? 5. 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. So it has 3 spots that it can bond. And we know that nitrogen is a diatomic molecule. It's N2. It's one of the Brinkelhoffs. So it forms a bond here, here, and here. And it's open spots. So it would look like this. Okay? Or if you like drawing the electrons that it's sharing, you could draw all 6 that it's sharing, and it would look like this. Kind of looks like I kind of almost move my smiley face a little bit more. Okay? Whether you draw your bonds as dashes or the actual electrons being shared, it's your personal preference. Okay? I will almost always draw them as lines. Okay? Okay? So, this is not in your notes. This is just bringing this together. Okay? If you have a single covalent bond, you're sharing 2 electrons. If you have a double, you're sharing 4. And if you have a triple, you're sharing 6. Just get used to, when you see the dashes, to count those as 2 electrons. Okay? 2 electrons. Now, I have to say that they drew this structure and this structure incorrectly. So, yeah. This should have had some lone... They didn't do their lone pairs right. I need to go find a better image, because I put that in there and I was like, that's not right. So those structures are not drawn correctly. Okay. So what about bond length and bond energy? Remember we said length is the amount of when the potential energy is minimized, and bond energy was how much energy it takes to break the bonds. Okay. So single bonds have a lower bond energy and a longer bond length. So the correlation is the shorter the bond, the higher the energy it is to break it. Okay? And if you go back to the effect of the nucleus on those electrons, it makes sense. A shorter bond means their nucleus is closer to those electrons. Okay? So, I'll let you fill that chart in, but basically triple bonds are the highest energy to break, and they are the shortest. Okay? And it makes sense that they're the highest energy to break, because you got to break 3 of them, right? You're not just breaking 1, you're breaking 3. It takes more energy. Okay? The examples at the bottom of that are ethane, and ethyne is how you would call those. The difference is just the bonds in the hydrogen. Still have 2 carbons. Yeah. Okay. All right, so everybody have that? So I believe that's going to take us to resonance structures. Yay. Okay, basically resonance structures are this. Okay, we've been drawing these Lewis structures, and I'm representing a molecule. Okay, most of the time, one Lewis structure is representative of it. But there are times when one is not covering the whole possibilities. Okay, and the example of this is ozone. Okay, and ozone is O3. Is its formula. So it means it's 3 oxygens. Okay. Now, later on, you'll learn how to tell, when we do molecular geometry, if it needs a double or a single bond. Right now, you don't know that. So I'm just going to tell you, ozone has 1 single and 1 double. Okay. But how do I know if that double bond is between atom 1 and 2 or 2 and 3? I don't. So I have to draw them both ways, and I have to say, there's one possibility, and I got to give everybody their lone pairs, because everybody has to get 8, right? But what if the double bond is between the first 2? So I have to show both possibilities. And we represent a Lewis structure by the double arrow between them. So that's showing that we're not sure which one it is. It could have resonance, is what we say. Okay? Because that's the only way we can represent it on paper. In actuality, it's like 1.5 bonds on each one in actuality. Okay? But we can't really represent that, so we do these resonance structures. Okay? Or we say that that molecule has resonance, meaning there's more than one way to show it. Okay? So that brings us to ionic bonding and ionic compounds. One of my favorite cartoons. If you're not a James Bond fan and you don't know anything about James Bond, it won't make any sense. Okay? But if you like James Bond, it's a take on that. Okay? Yeah. Taken, not shared. Okay? All right. Ionic compounds, remember, are composed of positive and negative ions. I told you I was going to be a long lecture today. I'm sorry. Partly because I'm adding an extra lab to this unit, so I needed to get this done. Okay? They're composed of positive and negative ions, which are cations and anions, and they combine so that the number of positive and negative charges are equal. So if you have 4 positive, you got to have 4 negative. They have to be neutral or electrically neutral, so to speak. Okay? Most of ionic compounds are crystalline solids. Okay? And they are between a metal and a non-metal. Metal and a non-metal. Okay? Everybody got that? Formula units are what we refer to as ionic compounds. Remember, we call covalent molecules or molecular, we call ionic formula units because they are not stuck together like a molecule is. They're basically opposites attract. Positive is being attracted to the negative ion. So we call those formula units. Okay? When we were doing the calculations with Avogadro's number, and sometimes it would ask you find the formula units, sometimes it would ask you the molecules, and sometimes it would say the atoms. Atoms is elements. Okay? If it says molecules, we're referring to a molecular compound that is covalently bonded. And if it says formula units, we're referring to an ionic compound. Okay? The electron dot or Lewis structure for ionic compounds, this time we're showing, instead of showing sharing, we're showing the transfer of the electron. Okay? So you'll need to draw this in. You've got the letters. There's an extra plus sign on the product side, so you can mark that out. But basically, this is being given right here to that orbital. Okay? So then I have a plus for sodium, because it gave away its electron, and now chlorine has an extra one, so it's negative. So that's how we would show for Lewis structure for ionic compounds, or the reaction of what's going on. Because they're not sharing, they're giving and taking. You'll have that. The characteristics of ionic bonds, okay? Remember, nature always, and I've said this like 4 times, so that might be something you want to remember, likes things in its potential energy when it's minimized, once its lowest form of potential energy minimized. So if it gives or takes in electrons, they can complete that octet, okay? In the case of sodium, it has 1 valence electron. So if it gives away that 1, it has an octet underneath in its core electrons, so it's more stable. Which is why we said you can never find group 1 metals free in nature, because they want to get rid of that 1 that they have so they can be more stable. Okay? They're in a crystal lattice structure, which is very organized. Okay? Very organized because it's a crystal. That's the arrangement at which the potential energy is minimized. They're alternating structures of positive and negatives. We saw that in the TED video, okay, that they're alternating between the positives and the negatives. And the lattice energy is the energy released when 1 mole of an ionic compound is formed from gaseous ions. Okay? It's energy released. Because it's more stable, so it releases some of its potential energy when it bonds. Okay? There are 2 types of ions. Monoatomic. Mono means 1, so 1, which is what we did today on the quiz. Everything was monoatomic. And then there's polyatomic, which is 2 or more atoms in an ion. Okay? What you need to know about polyatomic is that they're actually covalently bonded with a charge. Because if you look at these ones that we have listed here, they're all nonmetals, right? And I told you 2 nonmetals make a covalent compound. So they're covalently bonded, but the way in which they're bonded, they have a charge, so they're going to act like ions. So if you see a polyatomic in a compound, it's going to be an ionic. Okay, it's going to be ionic because they have a full out charge on that ion. Okay. So they're covalently bonded with a charge, but because they have a charge, they're going to act like an ionic bond. Okay. So that brings us last to metallic bonding. And usually you say last but not least, but in this case I'm going to say last and least because we do the least amount of stuff with metallic bonding because they're boring, so to speak, okay, in my opinion. So, but metallic bonding is weird in that their electrons do not belong to the individual atoms. They are called delocalized, and they share them amongst. It's like the socialism of bonding. They share everything. Okay, they share all their electrons. Okay, all right. So we call that a sea of electrons. Okay, because of that sea of electrons, that is why that they are able to conduct electric current so well, because the electrons are free flowing throughout the entire material. Okay, so they're called delocalized or sea of electrons. Usually we say sea of electrons. So they're not bonded to any particular atom. Now remember, this is just their valence, not their core. The core electrons belong to each atom, but their valence electrons are shared amongst themselves. Okay? Which is kind of strange, right? It seems weird that they can do that, but that is why they make such good conductors. Okay? Now this is between a metal and a metal. Okay? Just between a metal and a metal. That's why it's metallic bonding. Okay? The properties are your classic metallic properties that we're used to. Malleability, ductile, tensile strength, those things like that. They have a very high electrical and thermal conductivity, and it's because those electrons are able to freely travel throughout all of the atoms. They absorb a wide range of light frequency because many of them, because many of them have d orbitals, so they can absorb a wider range. And then they're luster or shiny, okay, because of the photoelectric effect. So when you see a metal shining, it's actually because electrons are being emitted off. Or photons, not electrons. Photons, excuse me. That was a big misspeak. Okay. And then I think we only have one more slide, might be two. Yeah, I'm sorry it's so long today. I don't like to lecture this long normally. All right, does everybody have that? Almost. Oh, I didn't even think about it. Okay? So, metal alloys, if I think this got left off on your notes, let's add that in. Normally when we have a mixture of metals, we call them an alloy. So things like brass, sterling silver, bronze, those are all alloys. So that's usually what we call metals when they're bonded together. Metallic bonding are alloys. Okay? Which we did that when we were in the classification of matter unit. Metallic strength varies with the nuclear charge of the metal. Oh, too far? Sorry. I apologize. Now we good? Okay. Metallic bond strength varies with nuclear charge of the metal. Your heat of vaporization is the amount of heat required to vaporize the metal. So you would expect that to be pretty high, right? It takes a lot of heat to vaporize a metal. And it is a measurement of the strength of the bond. In general, the higher the value, the stronger the metal. Okay? In general. Okay? I'm sorry, what? No, we're doing molecular geometry next week, so this is the last slide.